So let's get started. I think everyone pretty much is here. Like Tuesday, for home keeping stuff, for administrative stuff, you come to me after class. We will send out a file that everyone can fill out for those students that don't think they have enough CAD experience to do the assignment you have for Rapid Tech, okay? But so I'll talk more about that after the class, okay? Let's get started. So where we had arrived was right here. We've been talking about the fact that in mechanical machining, we have 4 different ways to go about things, right? It was milling, turning, grinding, and what else? Milling, turning, grinding, and what? What? Drilling. Remember, with the violin, drilling. Now, grinding was one that I hadn't shown you yet, but probably from what you saw so far, you could completely define what characterizes grinding. So in terms of energy domain, what we apply is obviously mechanical. Is it single point or multi-point? Multi-point. Will it be a more expensive or less expensive technique? More expensive, right? Because it's a primary, secondary, or tertiary technique? Tertiary, right? And we know the cost of a workpiece goes up the more you go to tertiary kind of machining techniques, right? One more thing. Is it subtractive or additive? That's a simple one. Subtractive, obviously, right? So with that, we're going to give a little bit of history of CNC machining, which is, of course, one of the foremost methods of mechanical machining. You will often see the word CNC machining. Where it comes from is numerical control, which is a method of automatically operating a manufacturing machine based on a code of letters, numbers, and special characters. Do you realize CNC actually only really started in 1977? And at that time, you can kind of see the cartoon up there, was in an open mode in the sense that you had a work table that could be controlled by a pulse train coming from your computer, and then a stepping motor that could position your workpiece where you want it. At that time, you were talking about reproducible steps, movements that this machine could make of 0.5 microns. That's kind of remarkable because where we are today is a couple of nanometers. So things have improved very, very fast. So, and it's the resolution of those steps that a machine can make that's of course determining how accurate your machining is. A big thing that needed to happen to improve the situation of the original XY tables, that was to go from open loop, as you can see there, to closed loop, as you see at the bottom. You see, it's not enough to just put the workpiece in a new position. You want to know, is it actually really there? And so you needed to have a position sensor that could feed back the position and then a comparator to make sure it is exactly in the spot that I intended it to be. Now, in the next slides, we will come to look at the different kind of CNC machines that are out there. First of all, in terms of how they operate, you could have a machine that goes point to point. In other words, your computer can say that the milling bit needs to go to that point and do something there. Lift up, go somewhere else. That's point-to-point control. Alternatively, you have continuous path controllers where you can drill into the piece and then just carve out the channel and you remain in contact with the workpiece. That is a continuous path controller system. And these continuous operating machines include milling along lines at any angle, milling arcs, and late turning, which would mean that you could basically turn the piece and also turn the drill, of course, when you wanted to. This comes to this 3-axis machining, 5-axis machining, and not 6-axis machining. Remember, I told you there's a specific reason why you will never have 6-axis machining. It will become clear from this slide here. The simplest CNC machine could be a vertical mill, as you can see on the left in the biggest square there, where basically your drill bit can come down and then your workpiece can move in the X direction, Y direction, and Z direction. These are the simplest, least expensive CNC machines. More complex CNC machines have extra capabilities. You can also rotate around these axes. Now you can realize if I rotate around the Y and X axis, I do something new. But what happens if I rotate around the Z axis? You're just drilling. That's the same thing, right? And so that's the reason why you have no 6-axis, right? Because if the drill goes around or you turn around the piece, it's the same thing, right? So that's why you have only 5-axis machines out there. Yes?
What if you want to put a slot that's not
Say that again?
X or Y axis?
Uh-huh.
Can you engage the 2 motors so you can have the bit move up at an angle?
Absolutely, yeah.
Yeah.
Absolutely. Actually, the last machine I will show does exactly that. The Fanuc Robo I does do exactly that kind of a... It will actually carve out a mask where you need to do that. Contouring, basically, that's what you're talking about. Yeah. This slide will be important for when you have that practicum on CNC machining, right? Because it will tell you in much more detail the process flow you will go through when you're faced with a CNC machine like these. The process flow will be to develop or obtain the 3D geometry of the model part you're going to be making using CAD. That's why we need to make sure that you all have a minimum of understanding of CAD. Then you decide which machining operations and cutter paths directions are required. And that's all computer assisted. Mind you, this machine might have up to 90 workpieces sitting there. It's almost like, okay, for this machining job, I need to go pick up that drill, or I need this work tool. And so the machine can go select those depending on the need that you have. So you decide which machining operations and cutter path directions are required. That's computer assisted. Choose the tooling required, also computer assisted. And then run CAM software. So what's the difference between CAD and CAM? CAD is computer-aided design, and CAM is computer-aided manufacturing. And more, these 2 programs are interlocked. So the CAM is interpreting the CAD, the design, and tells you how to machine it, what tools you will need. So you will then run the CAM software to generate a CNC part program, verify and edit the program, download the part program to the correct machine. It will even tell you, oh, you can't even do it on this machine. You need another one. And then verify the program on the actual machine and edit if necessary, and run the program, produce the part. You will not have to do this yourself. You will be guided through it by a CNC machine specialist, right? Because in groups of 20, unfortunately, I cannot have you all make your own part. If you guys are interested enough, I'm actually pretty sure that the operators are willing to give you some time, but you will have to do it by yourself, right? The same will be true, by the way, for 3D printing. There you will be a little bit more hands-on, but people that are really interested, there are now 9 student setups that you can use. And so actually people at Rapidtech will be very happy to give you access to that. So in both cases, it's a little bit your own motivation that will guide you. Do you want to know more? Well, you'll have to ask for more. Because this is a big group. So finally, on the CNC machining, in an integrated CAD-CAM system, the geometry and tool motions are derived automatically from the CAD database by the numerical control program. And so again, you will see this in great detail while looking at the actual machine while it's being carried out. This slide will be familiar because I'm kind of looping back to to some of the concepts I introduced in the first class. You all remember the difference between relative tolerance and absolute tolerance, right? What was the big deal there? We started recognizing that relative tolerance for very small parts and very big parts both start suffering, right? They aren't very good. I told you that actually you building your house will be about with the same relative tolerance as you making an IC line of 100 microns long. On the other hand, if you build something the size of a human hand, maybe a lens, you will find that relative tolerance is what? Worse or better?
-6.
Much better. It can be up to 1 part per million. And I told you, remember that curve, right? It was like a peaked curve that mechanical engineers define fine machining at what level? At 10 to the minus 4, so 0.01%. That actually means that integrated circuitry doesn't even qualify as fine machining for mechanical engineers. So it's kind of funny, right? Electrical engineers, we've always been saying we make these very small things, MEMS, nanotechnology, but actually traditional mechanical machinists, in terms of relative tolerance, are way better, actually by up to 4 orders of magnitude. So if you have someone bragging, I can make it so very small, you should say, yes, but how good can you make it? What is the relative tolerance? And maybe they'll shoot a red color. Right? So repeating that, mechanical engineers define precision machining as machining in which the relative accuracy, which is tolerance over object size, right? Let's say you have 100 centimeter and you're off by 1 centimeter, relative tolerance is 1%, right? So it's tolerance over the object size. But to do precision machining, that number needs to be 10 to the minus 4 or less. And in the case of integrated circuitry, how much was it? In the case of 100 microns, what did I tell you? About 1%. So way, way worse, right? So for comparison, a relative accuracy of 10 to the minus 3 in the construction of the house would be excellent. You will not achieve that. It is important to realize that while IC techniques and silicon micro and nanomachining can achieve excellent absolute tolerances. So that's the key. If you want to make something very, very small, you will not do it with big machine tools. You will do it with light writing, with lithography. But relative tolerance on that is not so good. So a nano machining can achieve excellent absolute tolerances. Relative tolerances here are rather poor compared to those achieved with most mechanical machining techniques. The decrease in manufacturing accuracy with decreasing size is rarely mentioned. And you know why that is actually? Because electrical engineers dominated the IC world. And they ain't thinking very much in relative tolerances. It's kind of different jargons. So putting electrical and mechanical engineers together, you can have some funny conversations. So the first kind of remarkable point in the CNC machining evolution was 1997, right, where equipment got introduced. Then in the 1980s, that's when some major progress was achieved, because machine tools became equipped with precision metrology. Remember what metrology is, right? These are the measuring methods, and these could be interferometry. These machines used laser interferometry and capacitance probe feedback controls. You remember 1977 open loop, and then in the 80s we had feedback control. So what I will do, that 0.5 micron accuracy we had at the time will improve. And it will improve fast, as we will see. Because in the 80s, we already got down to 0.1 micrometer. At that time also, a lot of that was done for the military in the beginning. That would be like Lawrence Livermore doing that kind of work. But in the 80s, these precision manufacturing methods were extended for industrial use, for cutting aluminum, which was used for making components for scanners, photocopy machines, and computer memory disks. Importantly, and this we actually really saw happening in the mid-80s, where the US kept on pushing micro and nanotechnology just with lithography. In Japan and in Germany, also in Korea, they kept on pushing other machining techniques just as well. We somehow got blinded that everything needed to be made with lithography. People that had been more traditionally in manufacturing, they kept a broader perspective. And for example, also in the 1980s, in Japan, they started cutting with very small diamond tools. For example, you know, a diameter of 22 micrometer. Do you remember where I told you the cutoff is between mechanical machining and lithography? I gave you a number where I said, look, if it's about that size, you could still do it with mechanical machining. But if it's below, you switch to lithography. What was that number? 100 microns. You can remember it, it's the same as the diameter of a human hair. Eh? So if things are much less than that, you will typically not use mechanical tools. But in Japan, they did 22 micrometer, and today they do even less. We will actually, at the end of this class too, see an example where a mask has been carved out with CNC machining, where features of 1 to 2 nanometers can be observed, can be differentiated. And this is kind of surprising, because you're going to say, look, how could I ever, with a 22 micrometer diameter tool, go to 1 or 2 nanometer? Thing will be this. In mechanical machining, you can do tremendously accurate things, but only in one axis, in the z-axis. The cutting itself of the piece, that will be much bigger. The mask will be, let's say, 1 millimeter. You can cut that. But the features that you carve out in the z direction by going up and down, like you were suggesting, at different angles, that you can do 1 to 2 nanometers. So when people compare lithography results and mechanical machining, you have to be very careful what you're really talking about. In photolithography, we can do the same small dimensions x, y, and z. In mechanical machining, only in one direction, z, x, or y. I hope you understand that. If not, by the end of this class, you have to ask questions and say, I still don't get that, why that is. Because I will come back to it at least twice today. Why this big difference in these accuracies between photolithography and mechanical machining. Things kept on developing, and actually, this is Professor Taniguchi, who as far back as 1974 introduced the term nanotechnology. You know, it had nothing to do with integrated circuitry. He determined that with mechanical machines, which is surprising, isn't it? When we hear nanotechnology today, how many people are thinking about mechanical machining and CNC machining? Not, right? We think about all other tools. The reality is, you can get there just as well. So he coined the term nanotechnology in 1974, and he used that to define ultra-precision machining. And how does he define that? Ultra-precision machining as the process by which the highest possible dimensional accuracy is achieved at a given point in time. It's him who predicted the accuracies along which the process or tools used to achieve would develop. You've seen this curve already before. These curves. These are the so-called Taniguchi curves, and what he's talking about, ultra-precision, is this bottom line. Now do follow that line, and so the 1977 point is in there, the 80s, and then now up to 2010, where we're actually in the nanometer range. This curve, do you remember what that was? The one that goes up? That's Moore's law. That is actually showing how we've been able to cramp more and more transistors onto a centimeter square, let's say, of silicon. That has exponentially improved and improved. The reason that that goes up is because I'm showing it in 1/, but both are a consequence of the same thing. Now we're going to see who paid attention in the previous class. What determines the fact that both these developments in mechanical machining and in integrated circuits were developing this way? What's controlling the progress?
Packaging between the IC circuitry that's fabricated with lithography and the packaging itself, which is micromachining. More accurate XY position stages.
Exactly. It's the position stages, isn't it? You remember now, right? And actually, I kind of highlighted it by saying, look, in the beginning, 1977, it was kind of like a poor XY position stage, right? There was not feedback. They kept on improving that and improving it. They made it vibration-free. And they got improvement both in mechanical machining and in electronic, lithography, right? So the key, binding this, is how good an XY position stage you can make. And it's common. Now, one more time, the difference between the two. In this case, you can make items with very small absolute sizes, right? Relative tolerance, in this case, is rather poor. Relative tolerance, in this case, is much better. But the absolute size is bigger, right? That was the first point. Now the second point, if you compare these two, what axis are you comparing? This here, these numbers have to do with one axis only. The line describing progress in the integrated circuitry is in all three dimensions. I see you nodding. Do you get that? Yes? And so let's prove this. Let's show this. Look at this. This is the top machine, CNC machine in the world right now. It's called the FANUC. Look, by 93, that's before this machine does better. 0.05 micron became possible, and today there's equipment that does better than 0.01 micron, and even nanometer step resolution, which is this machine. This no mask is made in this CNC machine. This is 1 millimeter, so to cut this out, you cannot make the whole thing very small, but in one axis, you can make it extremely accurate. You can make very small dimensions possible. So this, to carve out the eyes and the nose, that's nanometer resolution. But in the other dimension, XY, you have to remain bigger. Why? Because the tool size, remember? Maybe 22 micrometer. Do you get it now? So make sure, if you compare integrated circuitry devices and mechanical machine things, in certain aspects, mechanical machining can actually be better. In other aspects, integrated circuitry will do a lot better. By the way, we are not naive. By now, we know there's another reason why we would make things with IC technology rather than with mechanical machining. Tell me the keyword. This one is made in what mode compared to integrated circuitry? I want to hear the right. Thank you. Serial versus batch, right? Because if I make one of those, I made one. So this could cost you a lot of money, actually, to make this one. You might be working on this for an hour, 2 hours, and you got one. But if I do lithography, you have batch. And I could make 800 or 1,000 pieces all at the same time. That's another big difference. But mind you, what could I do with a machine like that? Instead of making one original shape, I could do what? I want to see if you guys start thinking as manufacturing engineers. You could make a mold. And then if you have a mold, you can pour in plastic, and you could make thousands, millions of these no masks, right? And then the cost is justified. To make a mold, it can cost a lot, right? As long as it's very good. And indeed, mold making is very typically done with CNC machining. Another mold making method we saw last class was called what? Lost wax method, right? But you could also do it with CNC machining. I told you another story on this FANUC machine, right? Told you it's actually hard to get those in the United States. In Japan, they would claim it is because it's difficult to send technicians to maintain it. But it could also be because maintaining equipment in your country allows you to make many products that make your country more competitive. And having new manufacturing tools and having some of you, motivated to come up with new manufacturing instrumentation, that's kind of the goal of this course. Because that will eventually determine the future of a nation. Can you make product? Can you make things that sell? I finish this class 2, and then we're going to do part of class 3 today, by this story about desktop factories. And I think I told you a little bit about that already, right? Look, if I'm going to make this no mask 1 millimeter, in diameter, why would I have a 1-ton machine? There's something wrong about that, right? And so more and more engineers start thinking about that. Why would I have a 1-ton machine to make a part, that weighs a milligram? And so they started thinking, we need to move away from that paradigm. Actually, they even plotted curves that showed the optimum relation between the size of a machine and the part you're making. And it's definitely not a million, It should be more reasonable. And so, again, especially in Japan, they came up with this idea of the desktop factory, DTF, and if you Google that, you'll see there's whole communities out there still today working towards factories that are the size of a tabletop. And that basically are the following. All you put into the factory is water, power, and materials, and out come the product. Often these factories are not alone. In this case, I have 1, 2, 3, 4 hooked up together. A little train set introduces a material block into the first factory. Something happens there, maybe CNC machining, goes to the next factory, it's cleaned, then maybe something is glued on it, etc. And depending on the product you want to make, you could kind of combine different desktop factories and make new products, right? So very, very modular. The US never invested in this. There was only one desktop factory made in Urbana-Champaign by my friend Corey Eman and Shiv Kapoor. And this kind of started ringing an alarm bell, even at the NSF. Are we missing out? If other countries do this, why not the United States? And so, to some degree, you could say that the Obama initiative for bringing manufacturing back to the US and all of this talk about 3D printing has kind of had its genesis in this. You see, this machine is not just rapid prototyping, right? It's really kind of like a small factory. And that is what everyone now talks about. They say 3D printing alone will actually never really solve the whole problem. Because often with 3D printing, when you make your own good, your own product, you will see it's too rough. So after the material, the outside, you still need to polish it, right? So what would that mean? That after you 3D printed it, there's another step necessary. That means the future will be small machines that do 3 things: multi-material, multi-physics, and multi-length scales. So I would like someone to translate this. Does that sink in? Do you know what I mean with that? Multi-physics, multi-length scales, and multi-material. So multi-physics, for example, I'll do subtractive machining and some additive machining. Not just additive machining. That's multi-physics. And by the way, I'm just reviewing proposals for the NSF. 20 proposals. They all have the same jargon. It's kind of sad in a way. Scientists are a little bit like lemmings. There's this osmosis of ideas, and then suddenly everyone about the same time jumps on it. But then you need to say, okay, who will really implement it? Who actually knows how to do it? Right, so we said multi-physics. Multi-materials is easy, right? You will see in the 3D printing machines at Rapidtech, you have at most 8 or 9 materials. That's not good enough. So part of your task could well be, if you stay in engineering, be it materials, mechanical, bioengineering, it will be to adapt more materials to, let's say, 3D printing. The third one maybe is the hardest to understand, although I alluded to it also in one class. The multi-length scales, what would that mean?
Building a big thing, tiny features.
Exactly, right? I was talking about the idea of a fractal. Like a tree has 21 orders of magnitude from the smallest feature to the biggest. Today, when we make something, the features distribution goes from a millimeter to a centimeter, that's it. So we would like to have multi-length scales. So you remember all 3? Exactly, right? So keep that in your head, because that could well be proposals that you're going to be working on, because I think this movement is global. And the people that come up the fastest with new machinery, new equipment that can do that, will be in the lead. By the way, that's another desktop factory. That's one that we saw in Japan. So it's hard to read, but each of these labels say what happens with the part at that specific location in the desktop factory. One could be etching, one could be deposition, another one could be cutting, etc. And then the idea is that with your computer you control the movement of the part from station to station. From label to label, the part moves, it's done, goes on to the next station. So while I'm calling up the third class, some time for questions.
Is there a reason why the US is not interested in the desktop factory?
So much money went into nanotechnology and almost all IC based. And how that has happened, probably because in a way it has remained our strongest industry, the power of an Intel, etc. It's one of the few areas where the US is still dominant. I would say that's probably was a big reason. Yeah.
By reducing the weight of the tool itself, by reducing the weight of micromachining
Right.
machine, are we also reducing the relative tolerance that a machine can have?
Yeah, you're up. That's a very good point, right? He's talking about that weight ratio. You know, if you make that very small thing, why you would have a machine of a ton? You cannot make the machine too small because it would become sensitive to vibration and therefore would become less accurate. So that's why people have studied that. They make kind of an optimum ratio for that. Any other question? Yeah?
What were the 3 length scales?
So multi-length scales, I said, right? Not 3-length scales. Is that what you asked me? Yeah. No, multi-length scales, meaning over many orders of magnitude, perhaps make a structure that's 1 meter tall and has features on there all the way down to 5 micron. Today, such machine does not exist. You know, they will do, let's say, from 1 centimeter to, you know, half a meter. And that's about it. Right? So multi-length scales, how would you do that? How would you make a machine that can cover all of these sizes? Yes?
What kind of things could you make with micromachining? Like, would you be able to machine channels for transistors or for besides that?
Okay, that's kind of interesting. I'm going to answer it with the proposal I'm just reviewing, right? Of course, I cannot give the name and the details, but people are now starting to think, look, the IC lithography, we will learn in a later class, is always planar, it's flat. You know, if you print transistors, it's on a silicon wafer, that's flat. With this machinery, you could actually put your transistors maybe on a cylinder, right? You could follow a shape. That's only one example. So you would have much, much more opportunity to print stuff on all type of surfaces. But at this point, you already recognize what is a big problem. It's serial, right? So how will we eventually multiplex that? I will show you some examples later on when you guys are all more mature in this business on how you could go about that. Yeah? So class 3 will talk about 2 more other methods of mechanical machining. So the first one we saw is using a workpiece, a tool that's harder than the workpiece. The 2 other examples I will give you are ultrasonic machining and ion beam milling, focused ion beam milling. So I'm kind of covering the whole range, because with CNC machining we can really carve out very big things, right? We can make motors, we can make huge structures. With ultrasonic machining, we will be blasting hard particles onto substrate to machine a structure. And with focused ion beam milling, we will create a plasma, extract ions, and bombard the workpiece with ions. So we will actually be machining with an ion. And actually today, focused ion beam milling is the most precise machining method available, mechanical machining method available. Better than electron beam machining. Now I said something. I want some of you guys to start thinking already. How could that be? if I machine something, my tool is not a hard tool, it's not a hard drill, harder than what I'm trying to carve out, but it's either an electron or an ion. Which one do we think will machine the smallest things? The electron or the ion?
Electrons seem smaller.
So he says the electron seems smaller. Who agrees with that? It's going to be a very strange answer. It's the ion. Does anyone know why? I can machine finer grooves with an ion that's so much bigger than an electron.
Because it has more mass, so you can hit it harder?
That's a purely mechanical answer. But it's not the right answer. Who said that? The Broglie wavelength. Fantastic. You see, the machining there happens because of the materials, the matter wavelength. And the Broglie wavelength of an ion, because it's heavier, is shorter. That is also why if you image something with ions, you can image smaller things with an ion than with an electron, because it's the wavelength feature associated with it that does the job. We'll come back to that, but so start thinking already about that. It's not always self-evident. Don't always jump to conclusions. Oh, more questions, guys? Facing a little problem here. Huh. That's not fun. Get me another question while I'm doing this here. No, no. Where I have seen it is in Olympus and in Sankyo Seiki in Japan. In Olympus, where it was used first is for the following. The lenses in the cameras on the cell phone became smaller and smaller, and human error to glue in that lens became bigger and bigger. And so they have now one of these microfactories, put the lens and then glue it in. That's kind of an example where it's already used, but not in clean rooms as far as I know. So this is class 3, and it's the final part on mechanical energy-driven manufacturing. And so, as I told you, we will cover 2 methods. Today, I will only cover the first one. That is ultrasonic machining, or USM. And then the other method that I maybe, depending on how many stories I tell, if you guys ask too many questions or I start telling stories, then I will not get there. So, sputtering and focused ion beam milling, FIB. So, what do we do in ultrasonic machining? Well, imagine that this is my workpiece right here, and let's say it's stainless steel or it's ceramic. It can be extremely hard material. It does not need to be conductor, it doesn't need to be metal. And here I have a work tool that moves up and down extremely fast. It's ultrasonically vibrated above the surface. Also, what I have is a slurry. I have water with small, fine abrasive particles. And through this movement of what we call the sonotrode, the tool, these slurry particles are agitated going back and forth and carving out the opposite size, shape of your workpiece. So let's look at how that works. So over here, this structure is it's the tool, it's the vibration structure, and it makes this end here go up and down against the workpiece. Here I have, in this case, an alumina slurry. So there's small particles of aluminum oxide that have to be harder than the workpiece. And by moving this structure up and down, let's say about 20,000 hertz, the small particles abrade the material away, and you eventually get a shape that's the opposite of, in this case, this cylinder. Same here, it's shown a little bit in more detail. The tool in this case has this shape. And here I have the slurry being brought in. This is the workpiece, and you can see I'm carving out the opposite shape of this tool. Mind you, this tool actually doesn't need to be all that hard, because it's not the tool that does the cutting, right? The cutting happens with these small hard particles that you bring in here. So,
The slurry, they also like cutting the surface of the tool as well.
say that again. If the
There's a slurry, like they're grinding the workpiece, right? But do they do the same thing on the tool too? So you wear out the tool
no.
on the same rate?
No, it will not. And this is actually a question that I typically reserve for the midterm. So write his question down. It's a very good question. And you can ask the same question for at least 3 of the machining methods we will talk about. Did you hear what he said? He said, but wait a minute, if this particle here moves up and down, why does it only abrade this one and not this one, right? Okay, I'm gonna take an innocent looking person. No, don't choke up this time. Scott? I don't know the answer yet, right? But so please, next week, Tuesday, you can tell us the answer. Who's volunteering for this problem? Are you? That's he looked behind him. You remember, this is all going to be on YouTube, right? From next week on, these are on YouTube. So, yes.
Would the tool portion have a harder surface finish, and therefore wouldn't degrade?
Well, this is actually, and the reason why he asked me, I made the remark that these often are actually not all that hard. They sometimes make them even out of carbon. So his question is very justified. So now you're intrigued too, eh? So, are you volunteering? You don't have to say it now. And if you have the answer, then I cannot ask the question for a midterm. Eh? Yes, you volunteer.
Is it because the tool's free moving and the ceramic can't move?
That's part of the answer. That's part of the answer. Good, very good. Yes?
Because mechanical machining in general is good in working in the Z direction? Is that part of the answer?
No, because that surface is also in the Z direction, right? So anyways, so far it's for the midterm, but it's good you know what to prepare for, unless someone gives the answer by Tuesday, okay? And you will see there's 2 other machining techniques. You could ask exactly the same thing. Why is my tool not being used up as fast? Okay, I will tell you, in EDM, electric discharge machining, you will have exactly the same question, right? And the answer is kind of similar for both cases. So I cannot give you, it's too good a question, so thanks. So in ultrasonic machining, USM, also called ultrasonic grinding, high frequency vibrations delivered to a tool tip, right? Oh, by the way, does anyone know how we will do this vibration? Piezoelectric. Who remembers what piezoelectricity is? So we're going to have that tool connected to a piezoelectric structure. Now, what is piezoelectricity? You see, manufacturing combines so many physics, science, materials, you know. People sometimes think it's low art, but it's not. There's a tremendous amount of knowledge in manufacturing. So piezoelectricity, remember that? So piezo is from the Greek, pressure, right? So if you have certain crystals, let's say quartz, and you pressurize the quartz, you will have electricity. And vice versa, if you put an AC signal on a quartz crystal, the quartz will expand, contract, expand, contract. That's what happens. And so it's that expansion and contraction of the crystal stack up there that makes this go up and down. But so let's read through it together. So in ultrasonic machining, USM, also called ultrasonic grinding, high-frequency vibrations delivered to a tool tip embedded in an abrasive slurry by a booster or sonotrode create accurate cavities or of virtually any shape that are negatives of the tool. Evident, right? Since this method, this is important. This is an example of a non-thermal method. Do you remember what I told you? A very big deficit of any thermal method on the workpiece was what? It was a 3-letter word. What might happen if a workpiece overheats? So, it's thermal. HAZ. What was that? Did you write it all down? HAZ, heat-affected zone. If you cannot tolerate any heat-affected zone, that's the technique. This method is non-thermal, non-electrical. It means it doesn't need to be a conductor. Non-chemical, obviously. It produces virtually stress-free shapes, even in very hard and brittle workpieces. So, for example, carbon, graphite, you could machine that this way. Very few other techniques will allow you to do that. Ultrasonic drilling is most effective for hard and brittle materials. Soft materials, you already got that probably. So if I instead of a hard material have a soft material, what will happen? The particle will bounce back, right? So it will be very ineffective. In a way, the harder the material, the better it will work, your technique. So soft materials absorb too much sound energy and make the process less efficient. So that hole here, 640 microns hole, was drilled by an ultrasonic drill. Almost any hard and brittle material, including aluminum oxide, silicon, silicon carbide, silicon nitride, glass, quartz, sapphire, ferrite, fiber optics, can all be ultrasonically machined. The tool does not exert any pressure on the workpiece, so you could call that drilling without drills, right? And we know that it doesn't touch ever the workpiece. And it's often made, and that's why it's such a good question, it's often made from a softer material than the workpiece, say from brass, cold rolled steel, or stainless steel, and wears only slightly. Gentleman in the corner, strange, right? The roots of ultrasonic technology, and this is now explaining the operation of this piezoelectric that was discovered by Pierre Curie around 1880, and he found that asymmetrical crystals such as quartz or Rochelle salt, potassium sodium nitrate, generate an electrical charge when mechanical pressure is applied, and conversely, mechanical vibrations are obtained by applying electrical oscillation to the same crystals. Ultrasonic waves or sound waves of frequency higher than 20,000 hertz. So that thing, that tool, vibrates at 20,000 hertz and slushes these hard particles onto the workpiece and carves out the negative of the shape of the tool. You could say it will be serial, but you could envision that you make a tool that has many shapes that you could all carve out at the same time, like here. So the tool typically vibrating at a low amplitude. So the amplitude, that means it's actually very, very small distance that goes back and forth. Only like 0.025 millimeter. Frequency, 2200 kilohertz. Is gradually fed into the workpiece to form a cavity corresponding to the tool shape. The vibration transmits a high velocity force to fine abrasive grains between the tool and the surface. In other words, there needs to be a little bit of space left, right, where the slurry can go and the particle can move up and down. In the process, material is removed by microchipping. So it's like a sandstorm, right? You kick off the material by hitting it with hard particles. So microchipping or erosion, it's also called. The grains are in a water slurry, which also serves to remove the debris from the cutting area. So the material you're cutting out is removed at the same time. And the high frequency power supply, also you could do piezoelectric or magnetostrictive. Magnetostrictive is the analogon of piezoelectric, but with magnets. And with magnets you can have the same effect, changing magnetic field, changing shape, and vice versa. So it's the equivalent effect. And so these, in the case of a piezoelectric transducer, stack is drives the tool, and the power is between 0.1 and 40 kilowatts. Abrasive slurry particles are 8 to 500 microns. They can be silicon carbide, aluminum oxide, or boron carbide. They're suspended in water or in oil. And the particle size and the vibration amplitude are usually made about the same. So in other words, that 0.025 micron amplitude, that would be then corresponding to the particle size. The particle size determines the roughness. That's kind of obvious, right? A bigger particle will make a rougher surface. And the speed of the cut. Very slow technique. So when you want to make things fast, this will not do it. So let's say 50 millimeter cube per minute. That's all. These are some other ultrasonically cut objects. This is a typical machine. It's not all that expensive, something like $20,000. Production rates of about 2,500 parts per machine per day are typical. If the machine part is a complex element, let's say a fluidic structure, a fluidic manifold in quartz, and it's bigger than a centimeter square, and the best material to be used is an inert hard ceramic, that's your technique. For example, if you want to do it in silicon, you would not use that. But if you have to make a fluidic structure, channels for flow of some liquids, gases, and it needs to be in a very inert hard material, and it's a rather large structure, that's a good solution. The next slide is a comparison table, and I want to see if each of you agrees with all of the statements. We have advantages of this new technique you're introduced to, disadvantages. So, advantages. Machining of any material regardless of conductivity. We understand that, right? Because it can be ceramic, it can be a superconductor, it doesn't matter, right? Other techniques like EDM, electro discharge machining, electrochemical machining, will only work with metals. This one will work with independent of conductivity. Another advantage, precision machining of brittle hard materials. So if you have something that is maybe like carbon, right? It's very difficult to machine carbon. It will break apart very easily. It will not if you use ultrasonic drilling. It does not produce electrical, thermal, or chemical defects at the surface. Key word here, it does not produce a heat-affected zone because there's no heat involved. It can drill circular or non-circular holes in very hard materials. Less stress because of its non-thermal nature. And then disadvantages without looking. Could you tell me some? Disadvantages. Slow. What else? Good. That's not even in there. And there, the second line is already kind of giving you a little bit of the answer, but not complete yet. We got half of the answer to the question why the tool doesn't wear as fast as a workpiece. Who gave half of the answer here? You did, right? And your half of the answer was? Yeah, the static versus the movement, but it does erode, so that gives you another clue. And then machining area and depth are quite restricted. So you can imagine, you cannot make a very big ultrasonic tool because the power you would need to bring this thing up and down, that just wouldn't apply, right? And the depth also, yes, can't really make, you will not drill very, very deep holes with that. So with this, I need to make a big transition to sputtering. And what I will do, I have enough time to introduce you some of the magic, I guess, behind plasmas. So what is a plasma?
Another phase.
It's another phase, yeah? Okay, but phase, he doesn't mean F-A-C-E, right? It's one of the phases of matter, yes? What is in a plasma? Because I'm going to need a plasma to do all of the machining we're going to do next. I need ions, so it definitely will have ions. It also has electrons and have neutrals. And so when we start the class next week, I will tell you about how a plasma is created, But for today, I only want you to focus on that table there on the top. You see that little table where it says ion energy in electron volt versus reaction. This is a little table that you should always know and keep in your head. It's a very, very important little table. What it says is that an ion, and let's say it's argon plus, and that ion has an energy of less than 3 electron volts, and it's going to hit this wall. What will it do? With 3 electron volts or less. All it will do, it might stick there. That's it. Now I'm giving it a bit more energy. I'm giving it 4 to 10 electron volt. You know what it might do? There's some dirt on there, some oil, some carbon, some oxygen. It might displace it. It starts sputter cleaning a little bit. This is already a manufacturing technique. Sputter cleaning with ions when you have an energy of about 10 eV. Now comes the more important one. Once I have between 10 and 5,000 eV, let's say 3,000 or 3 kilovolts. Now ion comes in. What it will start doing is sputtering. It will knock off atoms from the solid. So my workpiece now is an ion. That's my tool. And it's like billiards. I knock with my billiard ball the ion atoms off of my workpiece. So that's between 10 and 5,000. And then if I go yet higher, I go to 10,000 or 20,000 volts. You know what might happen? That ion has so much energy, it implants itself in the wall. So it digs between the atoms, and it might dope the material. How powerful? First thing, well, maybe not that useful. The ion sticks and it absorbs. That's it. Next one, ions for cleaning surfaces. If you have carbon or oxygen contamination, you come in with the argon ions and they clean it off. Third one, very important. I'm gonna sputter off top layers of gold, platinum, any material. Billiard-wise, mechanically, I'm kicking the atoms off. And I kick off at a certain rate, 5 layers, 10 layers, 20 layers. I dig into the material, I etch it. Finally, implantation. You all heard about doping of semiconductors. That's how it works. If the ions have yet more energy, they will implant themselves in the material. So actually, an ion beam could do 4 things for you. What a manufacturing tool. As long as we know how to create them, and we will create them when we get together again. This curve here, since I still have a bit more time, in a way follows up on these 4 items. Here it shows sputter yield. That means number of atoms I kick off per ion that comes in. Right? So yield, for example, if I have 1, that means each ion that comes in kicks off 1 atom from your workpiece. And this axis is the ion energy. So you guys already know, if it's less than 10, I'm not kicking off any atoms, yeah? I might be sputter clean. I need to be higher, I need to be between 10 and 5,000, and then this curve shoots up because I start sputtering. And now why does the curve bend over? You all know the answer. Why doesn't it keep on going? Because you start implanting, right? So this is an important curve for you. It kind of goes together with that little table. We have a little bit of time actually for questions. I think it's probably too much to start explaining how we create these plasmas and how we extract these ions to do the machining, because I'm going to do it on the board. I'm going to sketch it out for you guys. So if you have questions about the class so far, you can go ahead. Yes?
Where's the homework assignment?
There will be no homework assignment. Okay, so please do your best on the practica. That is very important. I feel sorry that you will be 20 per practica, but maybe in the future we will get more resources to make it into smaller groups, because you really should actually be able to do each of these things by yourself. Yes? Absolutely. I mean, silicon is a single crystal, and you dope silicon with implantation of ions, certainly. Yes?
So, for the USM, why is there no heat generated? Wouldn't the slurry cause friction between the workpiece and generate?
Well, there's the slurry, and the energy you put in it is not high enough. The rate is not high enough. It's a slow technique, right? So. But it's a good question, yeah. To really figure it out, you know, you would have to do the energy balance. How fast does the slurry remove the heat, and how much energy would you have to pump in to have enough friction, right? Yes, more questions. These are all good questions. You guys are following very well. I like that. Yes? Yeah, so on that one, there was a little bit of an alarm that you would have to have this already by Monday, and please. So I have asked Ed Tackett, the director of Rapidtech, to be here again on Monday. First of all, explain everything about all of the machines they have at Rapidtech, talk about the physics. Then it's only when you go there that you will be explained and guided through the process. So please don't be alarmed on that. That was really a miscommunication. And is Jacob here? Jacob? So Jacob, will you give a page now where everyone can write down who thinks they need a little bit of assistance on computer-aided design? Right, so if you think you need an extra class on CAD, we will set that up for you. But write your name down. So can you circulate a piece of paper for that?
So when do you need to submit the 3D file to Jacob?
Jacob, what is the projected date now for sending the file?
We have a pushback 1 week. So it would be Sunday, week 3. That's April 13th at 11:59 p.m.
Will that be enough time for those people that still need to do the CAD classes?
Yes? We do that with you. Is that enough time?
Well, we'll see when the CAD class can be given, right? So we will be flexible. So this is not, you know, to make you worried or scared about anything. So. More questions? If not, we'll call it a day. Any other questions here? Yes. Can you keep quiet?
Do you go into water cutting at all?
Say that again.
Do you go into water cutting at all?
Yes, yeah. Cheese cutting even, with water.
Is that qualified as mechanical?
It's mechanical, yeah. Yeah. It is, yeah. So this was a question about cutting cheese with water. What technique is that? Okay, before you go home, cutting cheese with a water stream. Serial or parallel? Mechanical? Electrical? What is it? Mechanical, yeah. Serial? What else could we say about it? Subtractive or additive? Subtractive. See, you guys are getting it, right? It's not that difficult. Very good. Secondary. Very good, thank you.